Okay, TJ, take it away.
Great. Thank you, James. And hello again, everyone. Glad to be working with you again today. Thanks for sticking it out throughout the week. Uh, Today, we're going to spend a little time working through one of the newest features of CompuCell. But I think it's pretty cool and it has a lot of potential for integrating with a lot of available data. Um, and the features are all about integrated Boolean network modeling in CompuCell 3D. And I believe I'm supposed to remind you that this is being, I think, live streamed and recorded. Um, yeah, so let's go ahead and just get into it. We're going to do a very brief overview of Boolean network modeling and what exactly that is for those of you who aren't familiar with the term or maybe have just never even heard of Boolean networks. We will very briefly survey what it can mean to integrate Boolean network models into multicellular modeling, like you've been doing in CompuCell. And then we will jump right in and do some interactive simulation building. We will build a multicellular model of delta notch signaling using Boolean networks. And then I have a couple of upfront warnings and caveats. First off, this feature set again is very new. And so some of these things have not been used by many people, including the TAs here who are available to work with you. So bear with us if you run into an issue and you get some support from someone who also may struggling with it, who also may be struggling with it. Just bear with us. If nothing else, you can always reach out to us individually afterwards and we can get you through any issues that you may experience. I will also point out, this is a very important detail. I am not an expert in Boolean network modeling. This is a relatively new field for me. There is a lot of experts out there. There are some people who've done some really good research in this field, even in my group here in Florida. But I am definitely not one of those people. So if you have questions about some of the nuances and intricacies of Boolean networks per se, there's a really good chance that I am not the person to answer those questions for you. However, if you reach out individually, I can point you in the right direction. In the meantime, I put a link in the chat. This is a link that you see on the screen there in the top middle. So this is a link to a specific section of the online documentation that is all dedicated to the stuff that we will briefly get into today. There is a lot more to this than what we will actually get into. And much of the subtleties that we won't have time to really dig into are all described in that documentation. So feel free to grab that link, maybe save it for later. If you're interested in these features, this is another good place to get more into the weeds on how this may be relevant to some of your projects or interests. Okay, all of that out of the way, what is a Boolean network model? You can see this depicted graphically in the top right. So Boolean network model is kind of similar to the kinds of reaction kinetic ODE models that you've worked with earlier this week using libRoadrunner and SBML and all of that. One of the main differences is how species or say objects in a model are represented. Most importantly, you can see here in this network in the top right, so there are various nodes representing various species, and they have all sorts of interactions. This is something fairly typical of what you might find in all sorts of different interesting biological papers. The important part here is that each of these species is not represented with a scalar value, as you've worked with using ODE models previously this week. All of these nodes, all of the species that are represented, they take values of true or false. Hence, they're Boolean. So a Boolean network model is a series of nodes that can take true or false values and then they interact with each other and affect each other's state, true or false, according to the biology that they're intended to represent. And these are some of there are examples of these kinds of interactions here. So you have nodes that can inhibit other nodes. You can have nodes that can activate themselves or can activate, say, other nodes. That's the whole idea. I'm not going to enumerate all the ways that this is that this readily connects to a lot of available data, but in a lot of cases, it's much more straightforward to integrate available experimental data with a Boolean network model as opposed to an ODE model. There's also lots of interesting theory. Again, much of the theory I am not particularly versed in. However, you can do all sorts of analysis to show things like cycling, where a network can repeatedly traverse through a trajectory in the state space. This is from a cell cycle model. And what do you know? You find a cycle. And you can also very nicely map out all the possible trajectories moving from one state to the next. We have Boolean network modeling integrated in CompuCell3D as provided by the stochastic Boolean network package MaBoSS. MaBoSS is written here in the top left. This is not a package that we maintain. I will put a link in the chat to the project page for MaBoSS. I think they pronounce it MaBoSS. So if anyone from Mary Curie is listening and are irritated by that, I apologize. So we have MaBoSS integrated in CompuCell such that you can create instances of Boolean network models, much like you've already done with SBML and antimony models, and then attach them to individual cells. So everything that you've done so far with reaction kinetic models using ODE models, the same features are available here, but for stochastic Boolean network models via integration of MaBoSS or MaBoSS in CC3D. And yeah, there's an example of this. This is a much more extensive version of the simulation that we are going to build here momentarily. But this is a simulation of delta notch signaling coupled with the cell cycle during wound healing. And see these plots shown here, see cells cycling between red and blue. These are real-time visualizations of various nodes in the underlying stochastic Boolean network model attached to each cell. And in this case, the states of those Boolean network models are actually being mapped to the type of cell that CompuCell understands. And as you've come to understand it this week, we will go through the exercise of actually doing a more simplified version of this, but we will do this sort of coupling where we will link stochastic Boolean networks attached to individual cells to cell type descriptors as CompuCell understands them. And you can see a small example here in the bottom left of what this looks like. So there's nothing exotic about this whatsoever. In fact, this was implemented in CompuCell long after antimony and SBML and all of that were implemented in CompuCell. So the intent here was to actually mimic that interface. So one thing that you should find as we dig into this is that you, when you go through the process of integrating these models that you attach to cells, you should find yourselves interacting with them, pulling data out of them, modifying them very similarly to how you've already learned to do with antimony and SBML models. Now I want to do a very brief introduction to how MaBoSS models are specified. Again, we will actually dig into this a little bit and build one of these ourselves, but just before we start coding, we'll do a very brief overview. So MaBoSS models generally are specified with two specifications. One is a network specification, which looks like what you see here in the bottom left. This is a specification defining the nodes in a network, and then the ways in which those nodes can either become high or become low. And for stochastic Boolean networks, also the rate at which those nodes can go up or down. And so that's what you see here in the bottom left. You can expect that momentarily we will define our own network specification, and we will use that to create MaBoSS models and attach them to cells. The other specification is a simulation configuration, and that's shown here in the bottom right. The simulation configuration just consists of defining initial states of various nodes, like shown here, I state. This is saying that the cyclin D node has an initial state of 1 or true or high, however you want to think about it. And then there's also declaration of, say, model parameters and other various things. We will get into this a little bit more, and we will actually use this a little bit to do some interesting things with our simulation. So go ahead and brace yourself. These are two things that we're going to specify that you've not seen yet. This is all MaBoSS specific. The details on what all is available in MaBoSS generally is available in the documentation provided by them, which again, you can find at the latest link that I put in the chat. I'll also say that even some of the things about MaBoSS I'm not particularly familiar with, and that's also okay. This is a great package, and I've had great experiences working with it, but at the end of the day, I'm also not an expert on this particular software package. I will say that the developers of this package are both very friendly and very supportive of their users. So if anything, I think you can count on reaching out to them to provide more information that maybe some of us may not be able to provide for you. All right, let's get to it. As we're talking through this introductory segment, you can go ahead and launch Player and tweet it if you haven't done so already. By now, I think you've already familiarized yourselves at least with some of the interesting aspects of delta notch signaling and why it's interesting in a multicellular spatial context. By now, I think James has sufficiently motivated why this is a really good biological system to use multicellular modeling and simulation. And so we're not going to dig into those details, just suffice it to say that we are going to implement the basic foundational aspects of the wound healing simulation that you see here in the bottom left. And so let's just get to it. We're going to start in tweet. So this is your last call. If you don't have tweet open, go ahead and get it started. We're going to start by creating a new simulation project in tweet with the wizard. I'm going to breeze through this a little bit because I think everyone has had some good practice by now creating simulations. So start by launching tweet, create a new project. Through the project wizard, you're going to create a Python plus XML project. And if you want to follow really closely with me, you can name it the same as what I will do. I'll name it DN model for delta notch model. This part isn't particularly important. The rest is. So as you're walking through wizard, you get to general simulation properties. We're going to do a two-dimensional simulation. Our lattice dimensions will be 200, 120, and 1. And the boundary conditions will be unchanged except for along the y dimension, or we will make the y dimension periodic. Otherwise, the only other thing you should need to update is to change the number of steps to 3,000. And we'll do a rectangular slab for our initial cell layout. Secondly, we're going to have 4 cell types. Medium is always there. We'll add the cell types inactive, delta, notch, and both. And as I said a few minutes ago, we will go through the procedure of mapping things in CompuCell to states of our network as attached to individual cells. And that's reflected here. So we are defining 4 cell types: inactive, delta, notch, and both. And we will prescribe the cell type of each of our individual cells according to these categories based on the state that we find their networks in. that doesn't make sense to you, that's totally okay. Just for now, suffice it to say that you'll have these 4 cell types: inactive, delta, notch, and both. Lastly, we're not gonna have any chemical fields, but we will add some cell properties and behaviors. In particular, we will have contact. We will use the volume flex. And we will use the cell neighbors property tracker. Contact, volume flex, cell neighbors. Give everyone 5 more seconds. After you've completed this, you can click your way through the rest of the wizard all the way to landing in Twedit with a template project. And that is where my project currently kicks off as well. So I'm going to do this in real time with you now. So start at the XML. First thing we will do is find our volume plugin. Susan asks where are the cell neighbors? It's to the top right in cell property trackers. Top right, second one from the top. All right, let's find our volume plugin. On my XML, it's at line 30. And we're not going to do anything particularly interesting here because we want to focus on working with the Boolean networks. So let's just leave our lambda volumes unchanged at 2 and change the target volumes to 36.
Where's the information of volume of the both cells?
Sorry, I don't think I quite understood. Oh, for the both cell type. Yeah, it looks like mine actually missed it somehow. That's okay. I can add it in really quickly. Good eye. Thank you very much.
Yeah, and don't forget the content. Yes. All right.
Let me do some coding in real time. Okay, so you all can make sure your volume plugin is updated. Lambda volume is 2, target volume is 36. And then next to your contacts plugin, which is where you see me furiously typing. All of the energy parameters should by default say 10, and that's what we'll use. So contact energy parameters of 10 all the way down, and we will set our neighbor order to 3.
Change your type ID on your new cell type.
Thank you very much. Was that Sharon?
Yep.
Thanks, Sharon. Okay, cell types, inactive, delta, notch, and both. The volume parameters, inactive, delta, notch, and both. All of those have lambda volume of 2 and target volume of 36. And both. All contact energies of 10. Neighbor order of 3. Lastly, should have a uniform initializer, steppable, maybe around line 63. We will put just one region all the way to the left-hand side of our simulation. And we'll make it span all the way from the bottom of the simulation up to the top. So from X and Y and Z of 0 and we'll make this 30 along X. And then up to the top of the simulation, 120 for Y and Z of 1. Last two details, we'll set our width to 6. And let's just start with cells of type inactive. This last one's not particularly important because we will actually control the types of cells throughout the simulation, but just to keep things brief, we'll just use inactive cells in our initial region. Okay, I'll give everyone 10 seconds. And then we'll move on to our steppable script. All right, let's do it. On to our steppable script. We will start by defining our MaBoSS model specification. You don't need to remove the NumPy import as I just did, but we won't need it, so I went ahead and erased it. It's fine if it stays. Let's start by first declaring our network specification. We'll do this in a multi-line string, which I believe you've done for some antimony models previously. We'll do the same thing here. Define both of our network specification and our simulation configuration in multi-line strings. We'll start with our network specification. If you want to follow really closely with me, I will name my variable bnd_str. And I'll go ahead and start a multi-line string. Now in our very simple delta notch model, we will have just 3 nodes. And those nodes will be named delta, notch, and NICD. I want to gloss over the biology here and focus on the programming and the modeling concepts at the implementation level. So suffice it to say that there will just be 3 nodes, and we can declare nodes again in MaBoSS in our network specification by first typing node and then the name of our node. I will start by defining my delta node, and we'll follow this declaration for a node with, for now, just empty curly brackets, and we'll write some stuff in here momentarily. For now, let's just set up our basic structure. Let's declare our 3 nodes. So I did node delta, now I'll do node notch. Put a placeholder, and node NICD. Now, primarily, what's really required in these definitions is a description of what drives each of these nodes to go up and to go down, or to become high, true, or to become low or false. And generally, what we want to define is a rate up and a rate down. And when we give this specification with these 2 variables defined to MaBoSS, MaBoSS will assign these rates to the constructed nodes. And essentially, all of the interactions among nodes in our network, they're all defined by describing rate up and rate down for each node. See a request to zoom in a little bit. Let me know if that's a little bit better.
Are those arbitrary keywords or, I mean, arbitrary variable names, or are those MaBoSS keywords?
MaBoSS keywords, great question. Yeah, MaBoSS will specifically look for a declaration of rate up and rate down for each node. And whatever you write there, that is the implementation of the interactions between nodes according to your model. When you say that one node makes another node go up, you would do so by defining such a relationship in rate up and or rate down. It's a good question. In our case, we'll follow a pattern that, in my experience, is really common with MaBoSS models, and that is to first just describe some variable logic for each of these nodes, and that logic will essentially say when a node is either high or low as a function of the other nodes in the network, and then we'll implement our rate up and rate down variables according to the value of logic. I want to include at least this detail in implementing these MaBoSS models because the pattern seems to be pretty common in my experience. So in this case, we will just generally define all of our rate up and rate down relationships through a variable logic defined for each node. In this case, for delta, we will say that logic, which is to say when delta becomes high or goes up, is when notch is low and when NICD is low. This is not Python syntax. This is maybe a bit unfamiliar to you in terms of how this is written. So believe me when I say that exclamation means not. So this says not notch. And this says not NICD. And so here logic says, or logic will be high when notch is low and when NICD is low. That's what you see written here. Now let's move on to notch. Let's define logic for notch. And here we will introduce an additional concept that we will get a little more into both in the simulation configuration and more importantly, when actually implementing code in our steppable. Here we will refer to a model variable. It's defined, or we will define in MaBoSS. So in our simulation configuration, one of the abilities that we have is to declare model variables, assign them values, and then refer to those variables in our network specification. Here, we will use a model variable called delta_ext. Now, two things to note here. First, we refer to a model variable that will be defined in our simulation configuration using the $sign. This is also MaBoSS specific. So this says refer to the value of the model variable delta_ext. For those of you who are really into MaBoSS, or not into delta notch signaling, or maybe could have guessed it, delta_ext, that's short for external delta. And in our model, what we will do is we will calculate the amount of external delta on each cell's neighbor in CompuCell, and then plug that into the MaBoSS model attached to each cell. So this is essentially a model variable that CompuCell will plug information into, that the network model in each cell will respond to. So in this case, we will say that the logic for notch is that it is true when the value of delta_ext is greater than 0. Notch goes high when external delta is greater than 0. Lastly, NICD. We will just say that NICD goes high when notch is high. So last survey here before we move on. Logic for delta. Logic is true when notch is low and NICD is low. Not notch and not NICD. Logic for notch is when our model variable delta ext or delta, so the model parameter will define in the simulation configuration. Delta ext is greater than 0. And logic for NICD, it's just, it goes up when notch is up. Urine asks, what does logic do? It's a great question. Logic is a local variable defined for the node that we will then use to write expressions with for our rate up and rate down definitions. All right, let's continue and actually finish the specification for our network. So let's start with delta. What we want to say is when logic is true, at logic, this is referencing logic here. When logic is true, rate up will be a variable fast, which we will also define in our simulation configuration. When logic is true, rate up is equal to a model variable fast. And when logic is false, rate up is 0. This also is not Python syntax. But the syntax here is that when this is true, rate up is this value. When this is not true, rate up is this value.
And what does the @ sign do?
Refers to logic. This is also a MaBoSS specific feature or syntax, I should say.
Yeah, I think of that sort of like a reference in C.
I would assume so. So the question, is it necessary to define rate up and rate down? Yes. At least I think. I'll say I assume so. I think it's possible maybe to have constant nodes. I don't see why that would be a problem, but for our purposes, yes, it is. Rate up and rate down is how MaBoSS will implement the interactions among our network nodes. The question about this $ fast, it's a good question. As a reminder, our second part of our MaBoSS specification, which is our simulation configuration, allows us to define the initial values of nodes, other details, many of which are not important for us at the moment, but another detail that is defined in the simulation configuration is model variables. And in this case, the $ in the network specification says refer to the value of this model variable that's defined in the simulation configuration. Okay, and let's write the complement for rate down. So for rate down, we'll say that when logic is true, our node doesn't go down. So its rate down is 0. Whereas when logic is false, our node goes down also with a rate equal to the model variable fast. And that's all this says, is that when this expression is true, rate up, or the node goes high with a rate equal to fast. And when this is not true, the node doesn't go up.
Are we allowed to add inline comments?
I believe so. With
I
I
mean,
believe
like,
so.
I mean, like to the right of the actual code.
Oh, I think so. You can try it. Okay. Now let's complete the other two. The other two should be relatively straightforward now that we've worked through the basic syntax. So for notch, we will say that rate up equals, and we'll also make this depend on notch's logic. Say that it goes up with a rate equal to our model variable delta underscore ext. Which again, this will be information that's provided from CompuCell through a model variable that we will declare in the simulation configuration. So when logic is high, rate up is equal to the value of delta underscore ext, otherwise it's equal to 0. And for rate down, we'll say that when logic is true, rate down is equal to 0, otherwise it'll be equal to our variable fast. Lastly, NICD, rate underscore up equals, you guessed it, make it depend on logic. When logic is true, we will also give it a rate up value equal to the model variable fast. Otherwise, it'll equal 0. And for rate down, we'll say that when logic is true, rate down is 0. Otherwise, it's equal to the model variable fast. I will put a copy of this network specification there in the chat. Feel free to grab that and replace if you got lost at any point. If nothing else, we can have the same typos and we can work through it together. We'll use this network specification momentarily. But recall that there is a second part of our MaBoSS specification, and that is the simulation configuration. We will also define the simulation configuration as a multi-line string. And if you're following really closely with me, I will name mine CFG underscore STR for configuration string and start a multi-line string. Now, the syntax that we've already used in the network specification mostly applies here. First, we will still reference, I guess in this case, declare model variables with the $sign. And in this case, we've been referring to two model variables in our network specification, delta ext and fast. Let's declare those here first. Let's say $sign fast equals 10. Fast will be the rate at which some of these rates will drive nodes up or down.
Sorry. In the node notch, the rate up, is that supposed to be fast instead of delta x?
No, in this case, the rate at which notch goes up is proportional to the value of delta ext. It's a good question.
Oh, okay. Okay, thanks.
Good question. Secondly, our delta underscore ext. We'll define that as a value of 0. Because as I've said a few times, in somewhat previewing capacity, this will be a model variable that CompuCell actually feeds into network models based on information about the cell's neighborhood. So for now, we'll set it to 0, and MaBoSS will rely on CompuCell to update this model variable for each network that we create. Lastly, can declare some initial states for our nodes. First, say delta to refer to the delta node, and then to set its initial state, and say dot iState. And we'll set all of the initial states equal to 0. So delta.iState equals 0, notch.iState equals 0, and nicd.iState equals 0. This says set the initial value of each of these nodes to low, false, 0, however you want to think about it. I will put this multi-line string in the chat as well, so that if anything, we can have the same typos. And let's continue on and get to some actual multicellular simulation work. So there are all sorts of interesting ways to particularize MaBoSS simulations as you create them and attach them to cells. We'll do just a little bit of work with these details. For one, you can set the pseudo-random number generator seed of each MaBoSS simulation when it's created. And we will use this capability momentarily. For now, let's go up to the top of our steppable script and add an additional import. In this case, we will import the random module. In a few moments, we will use the random module to generate some random numbers for us. And let's return a couple of lines, make a little space, and we'll enter random.seed. This will just seed the random module, make sure that we have fresh random numbers every time we run our simulation. And then lastly, without really getting into any of the details at all on the theory and capabilities of MaBoSS, there are particularities about how quickly stochastic Boolean networks are updated per simulation step. I want to ignore all of those details for now and rely on you to go investigate these details yourself as you are interested. For now, suffice it to say that we will use a variable time_tick to control the rate at which networks update per simulation step, time_tick, and we will set that to a value of 0.2. If we had more time, we could unpack this a little bit, but I will say for now, let's just use it so that you're aware of it. And as you become more interested in this, you can investigate it accordingly, or just email one of us afterward. Okay, so we imported random. We called random.seed and then added time tick equals 0.2. Let's continue and finally start working with some cells. So the code that you see on the left, this is a pattern that again is intended to mimic the antimony, SBML, and CellML interface as closely as possible for adding stochastic Boolean network model instances to cells. Self.add MaBoSS to cell. There's a description here for every keyword argument that is available. Most importantly, we pass a cell to tell CompuCell which cell to add a MaBoSS model to. We give it a model name just like with SBML models so that we can refer to them later. We provide our network specification and our simulation configuration, provide some integration information like a time step and time tick, and the seed. let's continue on and actually get into it so that we can actually do at least a little bit of coding. Let's go down to our start method for our steppable. So again, we're using the uniform initializer. So by the time we get to the start method in our simulation, our cells will already exist. So let's start by adding a MaBoSS model to every cell in our simulation. So let's do a loop over the cell list for cell in self.cell list.
Sorry, TJ, there was a question in the chat, which I also would be interested, was not certain about, which is what's the difference between time step and time tick? Is time tick a micro step executed multiple times per macro time step?
Yes.
Okay, so this is the same question that comes up with libRoadrunner and antimony, where you have a time step call in the steppable, which steps forward a certain amount of time, and then it calls a bunch of micro steps inside of that step.
Yep. I think there are some additional particularities with that I'm not sure are relevant to us, at least at this point. This is another one that I think for now, I would maybe behoove everyone to go read the documentation and or in the very least do a little bit of experimenting in CompuCell. For now, let's power on and add some MaBoSS models to CompuCell cells. So we're looping over the cell list for cell and self.cell list. Let's say self.add MaBoSS to cell. And start adding some arguments. So let's say add a MaBoSS model to the cell. Let's give it a model name of delta notch. Should be a string. This is how we will refer to the MaBoSS model that we've just created on this cell later, as we've done with SBML models previously this week. Next, we'll add our network configuration, has the keyword argument BNB_str, and conveniently, that is the same name as the variable that holds our network specification if you're following closely with me. Next, we passed our simulation configuration with the keyword argument CFG_str. Same convenience if you're following along with me. It's the same name as the model variable that has our simulation configuration. And then lastly, we'll provide a time step equal to our time tick, a time tick equal to our time tick. Again, please forgive me that we're glossing over some of the minutia here that we just honestly simply don't have time for. And lastly, we'll use an optional feature here where we will set the seed of the pseudo-random number generator in the MaBoSS simulation that's created with the keyword argument seed, and we'll say random.randint or generate a random integer. And we'll pass the lower bound, which is 0 in our case, and an upper bound of 1 billion. And I will write this as 1E9 as an integer. Very briefly, and again, check the MaBoSS documentation for more details on this, but time tick is it's like sub-stepping. For every simulation step, there are a number of times at which the network can be updated. Okay. I will add this block into the chat just in case anyone got lost or just wants to keep the same typos as me. I'm not sure how well that will format going from the chat in and out of a Python script, but you're free to try. Otherwise, we can continue on. What we've essentially done here is created an instance of our MaBoSS simulation for every cell in the cell list and added it to the cell. Give everyone 5 more seconds. Okay. On to the next thing. Very briefly, you can access the MaBoSS simulation that was just created from this call. I'll just type it out here directly. I'm having trouble with the degree at which I'm zoomed in here. If I want to retrieve the MaBoSS simulation that was just created here, I can say cell.maboss dot, then the model name that I gave, delta_notch. This is the MaBoSS model. Cell.maboss dot, and then the model name, delta notch. Just like you do with cell.sbml. And from here, you can access all sorts of things about the actual Boolean network. You can get the node values, you can set model variables. We'll use some of these features to do a bit of coupling between the Boolean networks and the multicellular simulation. Some of this is somewhat Pythonic in terms of interacting with the network as a dictionary. I think probably it's best to just dig right in because we can learn most of this by example. So let's just continue on and go down to our step method. Now, when we, for example, want to access the value of a node in a MaBoSS simulation that's attached to a cell, we can do so as follows. So I have in my template code that Twitter generated for me a loop over the cell list, and say I want to get the value of, say, the delta node in this particular cell. I can do so by saying cell.maboss.delta notch. So that's what I named it. And then, as if it were a dictionary, say delta to refer to the delta node, and then get the value of that node with state. What's returned by this call will give me a bool, either true or false. And that will be the value, the current value of that node in this cell's delta notch network. Now I can do something similar to access the model variables that were defined in the simulation configuration. This is a little more long-winded. You say cell.maboss.delta notch. This is all to just get to the delta notch network. And if I want to access the model parameters in the simulation configuration, I can say .network .symbol table. And this also acts like a dictionary. If I want to set delta ext in this cell, I can say cell.maboss.delta notch.network.symbol table. And I can read that, and that will give me a float. And I can also write to it. So we can set the value of that model parameter in this cell's delta notch Boolean network model. This is how we will establish communication between CompuCell and each cell's Boolean network model. So let's do it. Let's get right to it. The first thing we want to do is update the delta ext model variable in each of our cells. And this delta ext will be a count of the surface area of all cells in contact with our cell that have a high delta. It will be the sum of the surface area of all contacting cells that have high delta, hence external delta. So let's do it. First, let's start off in our cell loop. First, let's get the MaBoSS model for this cell. MaBoSS underscore model equals cell.MaBoSS dot delta underscore notch. That's the MaBoSS model that we created up here attached to this cell. Secondly, let's start a local variable to count the amount of surface area that this cell is in contact with for other cells that have high delta. Say num underscore delta underscore ext and set that to 0. We will add to this variable as we find neighbors that have high delta, or at least in a roundabout way. Now let's start a loop over our cell's neighbors. For neighbor, CSA, just short for common surface area. For neighbor, CSA in self.get cell neighbor data list. I think James is about to remind me privately in the chat that there are code snippets for this, and I apologize for not using them. I forget. One of the TAs would mind putting some hints in the chat for code snippets along the way. For those who don't like to write things out explicitly, I would invite you to do so and appreciate it very much. For neighbor and common surface area in self.get cell neighbor data list. First, we check and make sure that the neighbor we're given is a cell. And you can do this concisely by just saying if neighbor, and then get that cell's neighbor, MaBoSS model. Neighbor MaBoSS model equals neighbor dot MaBoSS dot delta underscore notch. And let's add the common surface area to our local variable. If that neighbor's delta state is high. Clever way to do this is by just saying num underscore delta underscore ext plus equals int of neighbor MaBoSS model delta dot state times CSA, common surface area. So we're doing a loop over the cell's neighbors, and for all cell neighbors, getting their MaBoSS models and then adding to our local variable the amount of common surface area times that cell's delta state, which is just a clever way to say add the common surface area if the neighbor's delta state is high. Having computed this, the num delta ext will be the value that we upload into this cell's MaBoSS model for the model variable delta ext, which, reviewing our network specification, it was here. Each of these cells has this network. A CompuCell will set the value of delta ext for each cell according to the computations that we just defined. So let's do it. MaBoSS underscore model was retrieved up here. Dot network. Dot symbol. Table. And then as a dictionary, delta underscore ext. Equals, and we'll make it a float of num delta ext. Here's this block of code in the chat as requested, so we can have the same typos in the very least. What we should find is that at every simulation step, CompuCell will do these calculations and update the variable delta ext in each cell's Boolean network. Now we have one more step, and then we can actually run a simulation and see if this works. Our very last step the player is to first time step every stochastic Boolean network in the simulation, much like you do with SBML models. Say self.timestep MaBoSS. This has the same effect on MaBoSS models as self.timestep SBML has on all SBML models. And then let's update the type of each cell based on the new state of its network. Now recall that our cell types were inactive, delta, notch, and both. All we want to do after time stepping all of the Boolean networks is just refresh the type of each cell based on the values of those cells' nodes. So let's start another loop over the cell list. You have code snippets, or if you like typing it explicitly like me, for cell in self.cell list. And let's first get the MaBoSS model of this cell. MaBoSS underscore model equals cell.maboss.delta underscore notch. And let's first just read the value of the delta and notch nodes. Let's get their state values. So let's say delta equals MaBoSS underscore model. And just like a dictionary, the key delta dot state. So we'll return the value state of the delta node. Secondly, do the same for notch. So notch equals MaBoSS underscore model, dictionary, the key notch dot state. And now we can just construct some simple logic here. If both delta and notch are low, then the cell's type becomes inactive. If only delta is high, then the cell's type will become delta. If only notch is high, the cell's type will become notch. And if both are high, then the cell's type becomes both. You don't have to follow exactly how I wrote it here in the example. However you want to implement that logic. Let's say if delta, if not notch, cell.type equals self.delta. Actually, this is old syntax. You can also say cell type dot delta. Either one will work. So if delta and notch, then cell.type equals self.both. If not delta and notch, then cell.type equals self.notch. And lastly, if not delta and not notch, then cell.type equals self.inactive. I'll give you this code snippet here. You're using that directly from the chat, and look out for issues with the tabs. I'll give everyone 15 seconds and then we will switch over to player and give it a try. If you've already completed this, feel free to go ahead and try it out and see what errors you get, if any. I'll give everyone 15 seconds. All right, let's try it out. So over to player. Go ahead and open that simulation file for the project you created here, or you in Twedit can use the open in player button, however you prefer. I already have mine preloaded, at least I think I did. We'll find out. Once you have it loaded in your preferred method, then give it a try. The two likely outcomes here are either that you have some typos that hopefully you can work out on your own, or they're not completely obvious. You can put them in the chat. Maybe I can address them just at the side of them, or a TA can get with you to help you work it out. Or if you were successful on the first try, which is exceedingly rare, then you should find some patterning similar to what you've done previously this week, but now controlling the types of cells based on the values of the Boolean network models you created and attached to individual cells. I seem to not have my both type. Oh, there it is. It's a weird update. That's a couple of people noting that both was missing from my table and player. Apparently I needed to click on it to get it to show up.
Mine didn't work until I added a line import random. Did you have it and I missed it?
Yeah. Yeah, we added that up here and then seeded and then defined the time tick. I'll point out very quickly, you should not see any growth here. There should be no cell, well, I mean, unless you coded something up waiting for me to stop talking. Unless, if you followed along with me, then what you should see is essentially what you see here. Just patterning, no significant changes in the morphology of the tissue, certainly no cell division or anything like wound healing. What we've done at this point is implement a stochastic Boolean network and then make those networks determine the types of those cells. Now, even just messing with this simulation as is can get pretty interesting once you start introducing things that say cause bulk changes in tissue shape. We're not going to get into those experiments today, but I will say from my own exploration of this model and developing from it, there's some really cool stuff that you can look into on the relationship between this patterning and emergent tissue shape and shape changes. James, how are we doing on time? It's 5:43 and
Fine.
fine.
Gonna hit run and see what it does.
That's it. We
You
get the
don't have
pattern.
any cell growth yet.
No, and that one, I have the link for that completed example, which is actually available in the distribution. But that one gets pretty complicated pretty quickly, so I didn't want to burn anyone out on first impression.
Because people were asking how to implement the cell growth in the chat.
See, there's a request to go back to my code. I will assume maybe down through here. Certainly we do not have time to do the cell division component. Certainly you have everything necessary to do so now, though. And to that effect, actually I have it right here. I'll go ahead and put it in the chat. There is the source code for the coupled cell cycle and delta notch model that we saw in the videos. We have that available on the repository in the collection of demos. The link to that project is in the chat. You should be able to download that and run it as is. And you should find that CompuCell spits out something approximately the same as the videos that we've seen of wound healing. I'll warn you that as you get into the code for that project, some of the names and even the structure of the network, there are certainly differences, but the principles are the same. The way to get the values of nodes, you can even set the state values of nodes, defining and interacting or modifying model parameters. It's all the same. These are the two basic aspects of the integration here. It's accessing and modifying the state of the network and then information about the model. I do have a couple of additional exercises planned. But at this point, what we have left for today is essentially connecting what we've learned so far to other CompuCell functionality that you've learned throughout the week. A very obvious one, at least to me, is visualization. So at the moment, if you've reached this milestone with me, then you're looking at cells with particular types, and it's interesting to know that you're driving the types of cells with the MaBoSS models attached to those cells, but how about actually visualizing the different node values of each individual cell? I think that's a useful exercise, so let's do that together. Let's move up to the start method of our steppable. Let's add a little space after where we added MaBoSS models to cells. And let's add a couple of tracking, scalar attribute tracking calls. I'm going to add a little comment here that says track MaBoSS node states. So that is exactly what we will do. Let's add 3 calls to self.track cell level scalar attribute. We'll do this 3 times, 1 for each of our nodes. 1, 2, 3. And we'll pass some arguments. So 3. We'll create a field called delta. And the attribute that corresponds to that field, we will call delta. And maybe you guessed it, we'll do the same for notch and NICD. Notch, field name equals notch, and attribute name equals notch. Lastly, field name equals NICD and attribute name equals NICD. Is that code in the chat? So 3 tracking fields, delta, notch, and NICD. Just name them the same as the nodes that we will inevitably track for each cell. If you're with me, let's head down to our step method and just anywhere in the second cell loop. Here we will upload the values of our node states into each cell's dictionary so that CompuCell can track it. Give a shout out to the people being creative, working with their MaBoSS simulations. See that creativity? That's pretty cool. Looks great. Okay, focused. Let's first complete what we started previously. We were fetching the value of our delta and notch states to determine cell types. Let's complete that with our third node, NICD equals MaBoSS underscore model, like a dictionary, NICD, and then dot state. And then just below that, let's upload these variable values into the cell's dictionary using the same keys or the same attribute names as in our cell tracking that we just added. So cell.dict dictionary delta equals delta cell dot notch and for NICD give me this code in the chat. It's what we just added. And let's try it out. Let's go back over to player. So if yours is still running or paused, sure to stop. Make sure in Twedit that you saved all of your scripts so that everything is updated for player. And then let's begin by pressing step. Then create some new fields. I'm sorry, some new graphics frames. We added 3 tracking fields, so let's look at 3 frames. Wow. Zoom is messing with my player's visualization. James, does that look really wonky to you?
Yeah, I noticed that earlier today and I wasn't sure. I also had some frozen windows that weren't updating.
Huh. Okay, good to know.
I haven't tried it when I don't have Zoom running though, so I'm not sure if it's a 4.6 issue or a Zoom issue.
Okay. Yeah, make a note
You'll
to look
see
at
when
that.
when you hit run, you'll see whether it's which it is.
Sure. Okay. So if you're following along closely with me, I created 3 more frames because we added 3 tracking fields. It's a little hard to see with my frozen weird frames, but set your frames to show each of your new tracking fields. I hope mine work. Oh, there we go. Okay, if you're seeing something similar to me, this may be a new bug. You may have luck refreshing by just doing a little bit of resizing on the frame. So this is how I've set this up. And even without running the simulation, you can already get a sense of what you're looking at. So here in this Delta graphics frame, see all the red. Each red cell shown here is a cell with high delta. And what do you know? When you look in the cell field, you find corresponding delta cells. And go ahead and let it go, let it run. Now you're looking at the node state for each of the 3 nodes in the network. See some great success in the chat. Looks awesome. Well done. Okay, we have 6 minutes left. I have one more exercise scheduled. And I'm actually just inclined to either stop now and leave a couple of minutes for questions. James, I'll let you decide.
You're
Howard.
welcome to overrun a little bit if you're able to, because we started a little late.
Okay,
But if you have to be somewhere at 6, by all means, it's your call on that. I would personally love to see the extra exercises. But
okay, we'll do this very quickly. Please keep in mind that these slides will be available. So any of this that you either got lost on or you just sort of typing what I told you to, that's, totally fine. You have access to all of the prepared materials here, so you can complete this on your own time. And of course, you also have all of our contact information. So I would invite, if not behoove you, to reach out for additional information as it interests you for either learning how to use all this stuff just generally, or even integrating it into, say, school or research projects. Okay, last thing. Let's do just a little bit of analysis and real-time visualization. Our last exercise will be to calculate the fraction of cells that have a high state for each node. We will add one new plot window, compute the fraction of cells that have each node as high, and then visualize that calculation in real time as the simulation progresses. So very quickly, I will give you the code as I type it in the chat. If you just don't feel like sprinting along with me, that's totally fine. I'm going to go up to the start method and add a new attribute to our steppable, because we want to keep track of what we create here. Say self.pop for population _win for window. Self.popWin equals, there are code snippets for this. I'm just going to type it out. James can give you the menu location. Self.popWin equals self.add new plot window. Start some arguments, give it a title, which we'll just say states. We'll give the x-axis a title. Step. We'll give the y-axis a title. So fraction. And lastly, we'll add a legend with the keyword argument config options, start a dictionary, say legend. True. I will give you the code for this very quickly if you don't feel like trying to race me. Now add a plot to this window for each of our 3 nodes, self.pop_win.add plot. And I'm going to be a little speedy and do copy paste. So it's mostly the same. First to say delta, and we'll give that a color of red. Second, plot for notch, and we'll give that a color of blue. And third for NICD, and we'll do a color of green. Here's the code for this. I'm gonna power on. We will venture down into the step method for this steppable and update or perform these calculations for each step and then upload the data to each of our plots. So down to the step method very quickly. After time stepping the MaBoSS models, I'm gonna first start a dictionary. Where I do these calculations, I'll first just track the number of cells that have a high state for each of the nodes in the network. First for delta, start that with a value of 0, another for notch, start with a value of 0. And lastly, for NICD, start that with a value of 0. I will just increment these values for every cell when I find that one of these states is high. There are numerous ways that you can implement this. I will just do so in a very simple manner. Just before updating the cell states, I will first say if delta, make a little bit of space here. If delta pop underscore states, delta plus equals 1. And maybe the pattern is obvious to you, maybe not. Either way is fine. If notch pop states, notch plus equals 1. And lastly, for NICD, if NICD, then pop states NICD plus equals 1. Give you an updated version of my step method from when MaBoSS models are updated onward. And lastly, using this pop states, now compute the fraction at the end of the step method. First, get the total number of cells. Num cells equals len of self dot cell list. And then just compute the fraction for each node and upload simultaneously. Self dot pop underscore when dot add data point. First for delta. Time is MCS. Was passed into step. And then just compute the fraction. Float of pop underscore states delta over num cells. This is redundant, but that's okay. And since we're just speeding through this, I will just very quickly complete this following the pattern, and then anyone wants it, I can upload the code into the chat. Thank you, James. James is providing code snippets since I severely neglect them. Okay, and let's just try it out. I put this code there in the chat. We're going to try it. If it doesn't work, we may just say goodnight. Stop the simulation if yours is still running or if it's paused. And then resume it by pressing step. And if everything worked, you should have a new window pop up for states and let it run. And we're done. You got to this point and you have something similar to what I have on my screen. Congratulations. If you do not, congratulations all the same. You've just learned one of the newest features of CompuCell and arguably one of the more complicated ones in under 2 hours time. So kudos to you. Everything we've gone over today, again, will be available in the shared folder. You all have our email addresses as well, including mine. Feel free to reach out about any of the details that maybe got by you or the details that we just didn't cover that might be of interest that you'd like to know more about. And of course, I'd invite anyone who's interested in actually working on developing these features or using them in their research, please, please, please reach out. James, I'll turn it back over to you. Thank you.
Okay, thank you, TJ. So, people, if you have questions for TJ, please ask, and please do fill out the completion poll. I wonder how many people, if any, have used Boolean network models before. It's especially for gene regulatory networks quite a popular way of doing modeling, because instead of the multiple parameters that you need for reaction kinetic models, you only need the one rate. And also, they run a lot faster than stochastic Gillespie models or ODE models. And so you can have much bigger networks. And sometimes also, they work pretty well if you only have qualitative information or semi-quantitative information about the network behaviors. So
I've
those
only
are
read about them in literature, either Boolean or Bayesian networks.
Hmm.
Yeah. I keep forgetting what the difference is between them too, but
Pedro, did you have a question?
Yeah. So, yeah, I sent an email to MaBoSS people, and they said to use this function that I pasted in the chat, to compute the power of something to some other thing. But it doesn't work. And I'm wondering if it's some version problem.
It's possible. We don't keep the MaBoSS distribution in CompuCell really close to the bleeding edge of what they're distributing. So yeah,
Alright.
it's definitely possible that they have new features out that are not available in the integrated version in CompuCell.
Yeah, because sometimes you want your rate to be, for example, a Michaelis function of some parameter. And then currently the only way I found was setting the rate in the Python side, then introducing as a parameter in the simulation.
Yeah, and I mean it's important to note that the features of MaBoSS that are available in CompuCell are a very limited subset of what that package can do. And I mean like an extremely limited subset.
Okay.
Yeah, that software provides a lot of really cool analytics features and I mean all sorts of interesting things that you can do with Boolean network models that are just not relevant for the way we're using MaBoSS. So if this is your first experience with that software, it's certainly what you've seen here today is a fraction of what all you can do with MaBoSS generally.
What I was wondering is, for example, sometimes you want two different rate ups depending on the states of nodes. So you can have two logics, you can define many logics, but you cannot define different rates and have one be prioritized over the other or something like that. So do you have a solution for this? I have one, but I don't think it's ideal.
Yeah, you're limited to what you can describe in that expression.
Yeah.
So you're free to write multiple logical statements. It may not be pretty, but it is possible to encode more complicated logic than the simple expressions we've used today.
Yeah. Yeah, that's all from me.
Okay, James, I actually do really need to run. So again, the slides will be available in the chat, and I'll one more time invite anyone to feel free to reach out. Anything that was either missed or went by you or anything else. Thank you again, everyone.
Thank you, TJ, very much.